Alright, so this is the second video for the Year 12 mark exam. So we're looking at question 2, and this is all the stuff on the quantum physics we've covered so far. So let's start off by looking at some energy levels. So this is a very typical energy level diagram. So you can see over here on the right hand side they're telling you what the quantum number of each level is, and over here on the left they've told you what the energy is at each of these quantum levels. So in this equation that we've been using for calculating the energy at each level, this equation here, so these numbers down here are your n's, so they're your bottom line, and these numbers down here on the left are these ENs, and obviously this is your ionization energy, but we don't need that for this particular question because they've already told you these energy levels, so this is something that happens quite a lot. So we've got a certain energy transition labelled by A, and if we then go down to look at the absorption spectrum, this A has led to getting this wavelength B on your absorption spectrum. Okay, so the first question asks, show that the frequency of B is about 4.6 times 10 to the 14. So, as you should know, photons are produced when an electron goes from a high level to a low level, so this transition here. So it's going from this amount of energy to this amount of energy. So what we know is the photon energy, so HF is equal to that energy transition, and we know by now that it will be the final state minus the initial state, and that number will indicate to you the amount of energy that the atom has lost. So when we take the magnitude of it, like you can see here, what that's showing you is the amount of energy the photon has gained. If we do that calculation, you get 1.89 electron volts of energy. And the other equation you should know is E equals HF. So what that means is the frequency is going to be the energy divided by your Planck's constant over here. So let's take your energy, you need to times it by 1.6 times 10 minus 19, getting a bit cramped over here, that should be a minus 19, and then divide that by Planck's constant, so our 6.63 times 10 to the minus 34, and that comes out as 4.56 times 10 to the 14, which is approximately 4.6 times 10 to the 14, which is what we were looking for. It's kind of a bit messy over here because my screen's a bit cracked on my iPad, but that should be 10 to the 14 there. Anyway, so then we want to calculate the wavelength of that. So for all electromagnetic waves, we can calculate wave speed in terms of the frequency and the wavelength. So if we want to work out what the wavelength is, it's going to be the speed of light divided by the frequency, which is 3 times 10 to the 8, because it's an electromagnetic wave, so they all travel at the speed of light. And we've also got our frequency we've just calculated, so the 4.56 number. Remember, using unrounded numbers in your calculations. 14, and that is equal to, so let's break that off so we know we don't get it mixed up. And if we put those numbers into the calculations, you get 6.58 times 10 to the minus 7 meters, because it's a wavelength. So checking the number of significant figures, the information we had from our energy level diagram, these two are both 3 significant figure numbers. The 1.60 is 3 significant figures, Planck's constant is 3 significant figures, speed of light is 3 significant figures, so your answer should be 3 significant figures as well. So nothing else should be given as that answer. Okay, so that's part, so let's move on to the second part of the quantum physics question. So then, we've got a hydrogen atom that's excited to level 4, and it's asking how many different wavelengths of electromagnetic radiation may be emitted when it returns to ground state. So let's sketch what that looks like. 1, 2, 3, and 4. So the different options, it could go straight back down to ground state, it could go down to 2, or it could go down to 3 like this, and then we would have this transition 2, and then from 3 it could go either all the way, or it could go down to there, and then returning to ground state would be the same as the one on the second path. So we have 1, 2, 3, 4, 5, 6, and therefore 6 different wavelengths. Okay, so calculate the energy in electron volts of the longest wavelength of electromagnetic radiation. So, longest wavelength means lowest frequency. Lowest frequency means lowest energy. So we want the smallest energy transition shown by this diagram. That's what it's looking for in this question. So the smallest transition is between the level, if you look back at the previous diagram, of the smallest energy will be given by the difference between the 0.85 electron level and the 1.51. You can do it with the others and check if you want, but this one is the smallest one. And if you put that in, remembering those are electron volts, that means the energy of the photon emitted will be 0.66 electron volts, because this is the smallest energy transition, which means the smallest photon energy, which means the longest wavelength. So then this one, in a fluorescent tube, explain how the mercury vapour and the coating of its inner surface contribute to the production of visible light. Okay, so there's a few stages to go through for here. So the first stage in this involving the mercury, so there are some stages before. So we have a filament which has a current pass through it, and that current gives the electrons energy enough to escape. The electrons are then accelerated by an electric field, and this is the point where we need to talk about in this question. So those electrons that are being accelerated by the electric field collide with a mercury orbital electron, and which causes them to become excited. So that's the first stage of this. So your mercury is excited, an electron in the mercury orbital is excited by a collision with an accelerated electron. So that's the first stage there. And then your mercury de-excites, emitting an ultraviolet photon. Okay, and identifying it specifically as an ultraviolet photon is important, so you have to say that. This needs to be in your answer. Just as in the previous one, you need to talk about the process of excitation. Okay, so then the next part is the coating of the bulb absorbs this UV photon. So that's the third stage, and then when the coating de-excites, it emits visible light, as you have there. So we've got the coating of the bulb absorbs the UV photon, and then when it de-excites, this is the process of taking multiple pathways back down to ground state, cascading down the energy levels, and it emits visible light. So just to quickly illustrate what cascading down the energy levels means. So the ultraviolet photon causes the phosphor to get excited to a very high energy level, so like somewhere up here, and the cascading process is this. So the process of taking multiple different pathways back down to a ground state like this. This is called cascading down the energy levels, and that's why visible light's produced, because we get these lower energy transitions in the de-excitation process. So that is the role that mercury and the coating of the tube play in producing the visible light. Okay, so that's going to be the end of this video. The next one will be looking at the circuitry questions, which were questions 7 and 8. 3 to 6 are going to be done by the other teacher.